Hello everybody, this is Dr. Sanchez, and today I'm going to be providing you with a tutorial of how to solve Hardy-Weinberg equations and also the reason why we go through this very elaborate mathematical problem, and especially because it's math. So some of you might find it a little bit difficult, but once you figure it out, I think it's fairly straightforward. And the purpose of Hardy-Weinberg equations is to help us determine, is it evolution? So let's work through a problem, and we're going to work with a problem with another bird that I love. You already know I love chickens, and I also love puffins. So we're going to imagine that puffins have two different alleles for leg color, orange and black. And we're going to also, for the purposes of our puffin population, establish that the orange allele is the dominant allele. So the problem we need to solve. You are researching puffins on the remote island of Fair Isle over the course of 3 years. In the first year, you count 1,000 puffins. And of those 1,000 birds, 97 have black legs. And that means all the rest have orange legs. At the end of the third year, you count 1,400 puffins with 123 birds with black legs. And your question is going to be, has evolution occurred? So to see if evolution occurs, we can use the Hardy-Weinberg equations to compare the populations for both years. So we know that we start off with 1,000 birds, and then we end up with 1,400. The change in the frequency of black legs and orange legs over time is just due to a natural increase in the population, or has something occurred to cause an evolutionary change. So let's start off with year one. We're going to compare data. So year one, we count 1,000 puffins, and of those 1,000 puffins, 903 have orange legs and 97 have black legs. Now, for the purposes of our Mendelian traits, we're going to use the letter C to refer to leg color, the alleles for leg colors. Since we're dealing with a hypothetical Mendelian trait, we need to determine how many of the flock are homozygous dominant, meaning that an individual has two copies of the dominant allele, capital C, capital C. How many are heterozygous, meaning that they have one dominant and one recessive allele, and how many of those are homozygous recessive, meaning they have two copies of the recessive allele. So given this information, which trait can we enumerate? And I think that this might have caused a little bit of confusion. What does that mean, to enumerate? Well, think of it in terms of, what does it sound like? Numeral, number, right? So which trait can we figure out from the information provided? So again, let's look at that puffin flock, and we see that 903 have orange legs and 97 have black legs. But with those 903 birds with orange legs, this is going to include those birds that have one dominant allele, and then all those other ones that have two dominant alleles. So there's actually two groups mixed up together. So from these phenotypes, what we can see, we need to determine the genotypes. So then we take those birds with orange legs. This is going to include all the homozygous dominants and the heterozygous genotypes. So as you can see there, if I can get a cursor. So if you see here, then those individuals that have two copies of the orange allele, of course, they're going to have orange legs. And then those birds that have one dominant and one recessive. And since these are Mendelian traits, then the orange allele is going to mask the black allele, and all these birds are going to have orange legs. Therefore, the only genotype that we can be sure of in terms of numbers are those with black legs, because we know that any puffin that has black legs must have inherited two recessive alleles. So the puffins with black legs, they're going to have one black allele from mother and one black allele from father, but we can be sure, since we know that the black allele is the recessive one, that this is an unmixed group, and we can actually figure out the numbers and utilize this in our problem. So step one of trying to figure out if evolution has occurred is to determine the allele frequencies. So we'll start with the frequency of the recessive allele, which is something that we can actually determine, right? So we can see very clearly that 97 puffins have black legs out of this population of 100. Or we can express this as 97 divided by 1,000, which will give us our value of Q squared. Dividing this will give us a decimal, which is 0.097, and we can round this up just for ease of multiplication to 0.1. Now this is the value of Q squared, and we need to know the value of Q. So in orange there, note this is the value of Q squared, and we need to know the value of Q for the equation. So to calculate that, right, to get to Q, we need to calculate the square root of 0.1 to get Q. So that's what we have to do next. So calculating the square root, we can do this a couple of ways. If you have a scientific calculator, then that will figure out square roots for you. You just put in the number that you want and hit the square root function, and it will give you the answer. But if you have, just a regular calculator, or you have a hard time figuring out how to use your scientific calculator, which is something that troubles me now and then, it's just as easy to type into Google your question and you'll get an answer. So just type into Google, what is the square root of 0.10 or 0.1? And Google will very kindly and quickly give you a response that the answer is 0.316, which we can then round up to 0.32. So our value for Q now then is 0.32. Once we know that, right, once we have the value of Q, we can then figure out the value of P. So remember that for the Hardy-Weinberg equation to work, we need to figure out the values of P and Q. We just figured out Q, so it's an easy thing to figure then the value of P. So since we know that Q equals 0.32 and that P plus Q must equal 1, then we can figure out by plugging in that value of Q to figure out P. So here we have it written out. So P equals 1 minus Q, or P equals 1 minus 0.32, which was the value we got from doing the square root of Q squared. Therefore, P is going to equal 0.68. Right, so 0.68 plus 0.32 does in fact equal 1. So what are P and Q again? So remember, P is the frequency of the dominant allele in a population, while Q is the frequency of the recessive alleles. Now, that is important to know, but again, remember that we know how many puffins are homozygous recessive. We need to know how many of those birds are homozygous dominant, who are going to have orange legs, and how many of those are heterozygous, who are also going to have orange legs. So this is what, having this number and using Hardy-Weinberg equation, we'll be able to figure out these other two groups. So let's plug our values into the Hardy-Weinberg multiplication. So again, very quickly, Hardy-Weinberg equation, P squared plus 2pq plus q squared equals 1. So what does that mean for a typical, really non-mathematical person like me? So we already determined that p equals 0.68. So p squared means that we have 0.68 times 0.68 plus, we go to 2p squared. This is going to be our heterozygous individuals. To get that, we're going to have 0.68 times 0.32. So PQ multiplied together multiplied by 2 is going to be the value for heterozygous individuals. And then 0.32 multiplied by 0.32 will give us the value of our homozygous recessives, and that has to equal 1. So if we multiply through this, we get the figures of 0.46 plus 0.44 plus 0.1 equals 1. And indeed, I worked it out, and it does. All these equal 1. So that helps us with getting through Hardy-Weinberg. But what do we do with this? So remember, what the Hardy-Weinberg equation gives us are the percentages of the total alleles that are homozygous dominant, heterozygous, and homozygous recessive, not the actual numbers of the individuals. So now we're going to have to convert the population with these numbers. So we started with a flock of 1,000 puffins. So if we take the numbers from Hardy-Weinberg, we can convert those decimals back to percentages just by moving the decimal point over to the right 2 places. So 0.46 will give us a percentage of 46% of our puffins are homozygous dominant, and 44% are heterozygous, and 10% are homozygous recessive. So what does that mean? If we take, divide 1,000 by 0.46, or we take 46% of 1,000, that's going to give us 460 puffins that are going to be homozygous dominant. That means that those puffins are going to have 2 copies of the dominant allele. 44% are heterozygous, so 440 puffins are going to have 1 dominant allele and 1 recessive allele, and then 10% are homozygous recessive, and that comes to 100 puffins. And if you'll remember from the start, we started off with knowing that 97 of our puffins had black legs, but because we rounded up, it rounded up a little bit to give us the number 100. So just take that into account, that we're squishing the numbers a little bit just because we're doing some rounding up. If we didn't round up, it would be closer probably, but close enough for me. Now let's look at our flock from year 3. Let's do the Hardy-Weinberg equation for the puffins that we count up in the 3rd year. And we see that our flock has increased to 1,400 puffins. And that's a big yay, because birds across the globe are endangered. And so we now have an increase in the size of our flock. And we look at our puffins and we count them up, and we note that 123 have black legs. And it's important to remember to count the ones with the black legs, because they have the recessive alleles. They are homozygous recessive. They have 2 copies of the recessive allele, which then will help us to figure out our Hardy-Weinberg equation. So we can use the Hardy-Weinberg equation to determine if evolution has occurred. And we're going to do this by comparing the numbers, the percentages from year 1 to the percentages in year 3 to see if there's been a frequency in the alleles. All right, so remember that change in allele frequency over time is evolution. So we're going to take a snapshot from year 1 and a snapshot from year 3 and compare and contrast to see if we can see the flock has increased, but that doesn't necessarily mean that there has actually been a change in the alleles. it could have stayed the same. So we need the Hardy-Weinberg equation to figure out if there has been a change in the frequency of alleles. So again, we know by counting up the birds that Q squared is equal to 123 birds out of 1,400 which have the homozygous recessive trait of black legs, which is equivalent to, if you divide 123 by 1,400, it gives us a number of 0.087, rounded up, and we're going to get 0.09. That gives us the value for Q squared. We take the square root of 0.09 to get Q. And when we do that, and again, you pop it into the Google or you use your scientific calculator, and we get the square root of 0.09 which is going to be 0.3. All right, so then again, P plus Q has to equal 1. So therefore, P equals 1 minus Q, or P equals 1 minus 0.3. So therefore, P must equal 0.7. P plus Q equals 1. So 0.7 plus 0.3 does indeed equal 1. Now that we have the values of P and Q, we can pop those into the Hardy-Weinberg equation, which again is P squared plus 2PQ plus Q squared equals 1. And again, to remind you, P squared, this is going to be the frequency of puffins that are homozygous dominant. 2PQ is going to be the frequency of puffins that are heterozygous, and Q squared is going to be the frequency of puffins that are homozygous recessive. And 1 equals the total population, right? So our figures, we pop them in again, so we can, P squared is equivalent to 0.7 times 0.7 plus 0.7 times 0.3, so P and Q, 2PQ times 2, plus 0.3 times 0.3 equals 1. So when we work that through, then we get these numbers. So P squared is equivalent to 0.49, and then 2PQ 0.42, and then Q squared is 0.09, which equals 1. So rendering that into percentages, what that tells us is that 49% of the flock is homozygous dominant, 42% of the flock is heterozygous, and 9% of the flock is homozygous recessive. And so those are percentages, not how many. So we have to then use our total number of birds to figure out how many. So for P, 49% of 1,400 is 686 birds. The 2PQ ended up being 42% of 1,400, and that is 588 birds, and 9% of 1,400 equals 126. And again, there's a little bit of a discrepancy because of rounding up. We counted 123 birds, but by doing the equation with rounding, it turned out to be 126, and that is close enough for horseshoes and hand grenades here. So is it evolution? And how do we determine that? We look and compare the percentages or the frequencies in year 1 with year 3. So in year 1, using the Hardy-Weinberg equation, we found that 46% are homozygous dominant. And in year 3, 49% are homozygous dominant. Year 1, 44% are heterozygous. Year 3, 42% are heterozygous. Year 1, 10% are homozygous recessive. And year 3, 9% are homozygous recessive. And we can say that yes, indeed, evolution has occurred, because over this 3-year period, there has been an increase in the number of dominant alleles over time. over time, the orange allele has increased in frequency. And it's interesting to compare and contrast so that there are percentage-wise, there's a greater percentage of the dominant homozygous dominance, 49%, but the frequency of heterozygous birds has decreased in year 3 from year 1. And then likewise, when we look at those birds that have black legs, that there were 10% of those back in year 1, and in year 3 there are 9%. So something is going on so that there is a net increase overall in the orange alleles, so that they are more favored for some reason, and then those with the recessive alleles, homozygous recessive, well, something has not been favoring them. So what now? What do we do with this information? So Hardy-Weinberg equation, we use this evolutionary biologists and evolutionary anthropologists. We take this kind of data in order to generate hypotheses. So just looking at that data, it tells us that change has occurred. Evolution has occurred, but we're never satisfied with just knowing that it occurred. We also want to know why. So the importance of the Hardy-Weinberg equation is that it gives us a way to measure whether or not evolution has occurred. So it's obviously we can see that the numbers of birds has increased from 1,000 to 1,400, but we need to actually know the frequency of alleles to determine whether or not that there is something going on to prefer one allele frequency over another. Right, so once we observe that evolution is occurring, well, then we can try and figure out the big question, which is why. And one of the most important elements of being a scientist is that you remain in that 3-year-old stage of always asking why. So our hypotheses, we can generate hypotheses to try and determine why there was evolution occurring in our flocks of puffins. So again, remember, there are many factors that drive evolution, and these include mutation, natural selection, genetic drift, and gene flow. And your chapter talks about all of these, and you should know the difference between these different forces of evolution. So if we were going to compare year 1 with year 3, we could generate 4 competing hypotheses to explain the evolution of this puffin population based on the 4 forces of evolution. So did the alleles did the dominant alleles increase over time due to mutation? Was there a reduction in the recessive alleles due to natural selection? Was there a change in allele frequency due to genetic drift or due to gene flow? So we have at least 4 competing hypotheses that we can try and evaluate and compare and test. So that's the end of my tutorial here, again with a lovely picture of orange-footed puffins, which I think that's just what they are. I don't actually think that, it works on a Mendelian case, but I just wanted to use a hypothetical that would help us to, figure out Hardy-Weinberg and also give you an idea of why we bother with this complex and often difficult to, work through equation. So we do it because it helps us to measure change over time. And then once we do observe that change has occurred, then we can try and explain why it happened. And we are going to try and explain what happened by testing hypotheses, eliminating those hypotheses that don't fit the data, and then proposing a theory for what has occurred to change the frequencies of alleles. So thank you very much for attending my TED Talk, and I will see you later. Bye-bye. Thanks a lot.